All right, let's take a look at another example. This is from the textbook. Okay, what we have here is a uniform cylinder of mass m, radius r. Okay, mass m, radius r. It is attached to a spring constant K, a massless spring at its center. And it can roll back and forth on the horizontal surface. It rolls without friction, okay? I'm sorry, it rolls without slipping. That's what I should say. If an object rolls without slipping, we know this is called pure rolling, and that requires a friction here, right? What kind of friction is it? Is it kinetic or is it static? Well, if it rolls without slipping, then this point doesn't move at all, right? Everything is rotating about point A, so point A does not move. Therefore, that should be static friction because there is no rubbing going on between the cylinder and the floor at that point. There is no relative motion, so it's actually static friction. Okay, in equilibrium, the spring is neither stretched nor compressed, right? Now, what happens if I pull the cylinder to one side or push it to the other side? Either way, I move it out of equilibrium, all right, and let go of it. Then it's going to start rolling, back and forth, back and forth, back and forth. What I want to show that this rolling motion is simple harmonic, and that is if you focus on the center of the ball, center of the cylinder, the center of the cylinder, the center of mass, goes back and forth in a simple harmonic manner. How does one show that? Well, I want to use this example to show you both methods. Okay, method number one is force or torque, and method number two is energy. So you can compare which method is superior in this case. First of all, if I want to use force or torque approach, okay, that's the first kind of approach, approach A. Where should I start? You know, this thing has to do with rotation, and when it comes to rotation, you know we have to look at some sort of torque equation. But of course, it also has translational motion because that point is actually moving, the center of mass actually is moving, so we also have to use Newton's second law for the center of mass, right? So it's a combination of rotation and translational motion. All right, let's look at the net force and let's look at the net torque. As far as the force is considered, how many forces are exerted on the cylinder as it rolls? Okay, at equilibrium, the spring is neither stretched nor compressed. The center of mass here is at the origin of a coordinate system. Now imagine this thing, the center of mass moves this way by an amount x, which means the spring is getting longer by an amount x, right? If that's the case, the spring is going to fight back with a force negative kx. Okay, so I'm going to draw a free body diagram for this thing, right? There is a force negative kx. That's from the spring. Vertically, of course, you have normal force and you have gravity. They cancel out. So that's boring. I'm not going to be more about it. I only consider about horizontal motion. Is this the only horizontal force exerted on the object? Well, if that's the case, there's no friction here whatsoever. What do you think the thing's going to do? Is it really going to roll? Nah, it's just going to slide, right? Back and forth without any rolling. In order to roll, we need a friction. It's static friction at point A. The question is, what is the direction of that friction? All right, good question. Now, think about it. Suppose we start with the cylinder somewhere on this side. Okay, so the spring is stretched, right? If the spring is stretched, then you let go of it. The spring want to pull it back. Now, as it is pulled back, it accelerates. Okay, it accelerates. So the center of mass is going to go faster and faster and faster. But remember, this is pure rolling. If it's pure rolling, then the faster you move, the faster you also have to roll to keep up with it, which means there is an actual acceleration or rotation this way. So it's actually going to roll this way, okay, and faster on its way back to equilibrium. that requires an angular acceleration in the clockwise sense. And exactly who is providing you with that angular acceleration? Well, you can say, well, it's the force through the center of mass, right? Sure, no problem. If you look at point A as a reference point, then the only external force providing torque is this force, negative kx, and actually does provide you with a clockwise angular acceleration. Not a problem. But on the other hand, if you focus your attention on the center of mass, and let's apply the torque theorem about the center of mass, okay, what would you get? Well, then of course this force has no torque, N has no torque, mg has no torque. Somebody else must come up with a torque. And who is that somebody else? Well, there has to be a friction here, right? At the pivot, at the center axis of rotation. What is the direction of that friction? Well, the direction of friction is such that it has to provide a clockwise torque about the center of mass. So is it forward or is it backward? Well, it has to rotate this way, right? So the friction has to be like this, Fs. Okay, so we know that has to be the case. How much is that friction? We don't know. But suppose we know what friction is, then the net force in this direction, okay, horizontal direction, can be written as Fs minus Kx. I'm using this as a positive direction, right? This positive direction equals mass times acceleration, right? M times that. Okay. Now, unfortunately, that doesn't solve the problem just yet, because I don't know what Fs is. How do we figure out Fs? Well, this is only for the translational motion of the center of mass, right? There is no mention of the rotational aspect. How about if I apply the torque theorem to study its rotation? You can apply torque theorem to two kinds of points. One is a fixed point, the other is the center of mass. If you apply torque theorem to the fixed point, what is a good point? Well, how about point A? Because it's pure rolling, point A is not moving, and therefore everything is rotating about point A. I can apply the torque theorem to that point. Okay, now if I did that, then the nice thing is Fs does not appear in my equation, right? So that I don't have to know what it is, because it has no torque about point A. The only force providing the torque is this, Kx. All right? And then, so let's see, what kind of torque does this thing provide? Well, the force is negative Kx, right? And the lever arm, using point A as observation from here to there, that's R. So that is the torque. And what is that equal to? It must equal to I alpha, according to the torque theorem. What is I? I must be measured from the observation point, which is point A. Okay. And what about alpha? Well, alpha is the angular acceleration. Here, this is the linear acceleration. You know, these two are actually related. In what sense? Well, it's pure rolling, right? And therefore, alpha must equal to A over R. Okay. If we plug this in here, then we get IA times A over R. And that A is the second derivative of x. It's the linear acceleration of point O at the center of the cylinder. When I take a close look at the second equation here, this thing alone can actually provide me with a solution to this problem, because I pretty much know everything else. The only thing I didn't know here was Fs, but it does not appear in the second equation. So if I rearrange the second equation a little bit better, you can see better what I mean. What I'm going to do is move this R over to the other side, okay? So I have negative Kx equals IA over R squared, right? IA over R squared. And then here you have the acceleration, which of course is just the second derivative. All right, take a good look at this equation here. How does that compare with simple harmonic motion equation we've learned for a simple mass spring system without any rolling going on? That would be equal to negative Kx equals MA, right? We learned that before. Okay, take a look at these two equations. What do they have in common? The left-hand sides are exactly equal to each other. The right-hand sides, you have acceleration here, and you have acceleration there. The only difference is that the mass m is replaced by another constant, IA over r squared. Okay, so we know that this leads to a simple harmonic motion. Then, of course, so must that, right? And exactly what does that lead to? Well, all we have to do is replace m with the effective mass, which is IA over r squared. And k is still k. There's nothing different. So I conclude that the cylinder does move in such a way its center of mass executes a simple harmonic oscillation. And here is the period of the simple harmonic oscillation. T equals 2 pi times the effective mass, okay, over the effective spring constant. The effective mass, as you learn here, m is replaced by IA over r squared. Okay, IA over r squared. And the k is still k. Exactly what is IA equal to? Well, IA is the rotational inertia about this axis. Okay, it is related to ICM, which is rotational inertia about the center of mass. You recall the so-called parallel axis theorem, IA equals to ICM plus what? mr squared, right? R is the separation between these two axes. So when I plug this in, I get T equals to 2 pi IA over r squared, okay, and then divided by k. Now, IA is ICM plus mr squared. ICM itself, that depends on what kind of object it is. It doesn't even have to be a cylinder. It can be any uniform object whose cross-sectional area is circular. It can be even actually a solid sphere or hollow sphere, whatever it is. But for a cylinder, we know what that is, right? A uniform cylinder radius r and mass m. ICM is 1/2 mr squared. Okay, so this is 1/2 mr squared plus another mr squared. That's 3 over 2 mr squared. Okay, you cross out that r squared, you got 3m over 2. This is the period of that motion. Okay, how does that compare with a block that simply slides without friction back and forth, attached to the same spring if the mass of the block is also m? Well, that would be 2 pi times the square root of m over k without that 3 over 2, right? But this is greater than that, you see? 2 pi than 2 pi m over k. That means when we don't have just a sliding block without friction, rather we have a rotating cylinder, okay? The period is longer than the case of a block sliding frictionlessly back and forth. It takes longer time to complete one revolution. Does that make sense? Well, yes, because once you have rolling, pure rolling going on, there must be a friction. And you see here, friction is against the restoring force. The spring want to pull you this way, the friction is against that, and that means you are slowed down, okay? Therefore, it takes longer time to finish than before. So you see, we solved this problem using torque approach. It is also possible, and I want to leave this as an exercise for you, instead of using point A as a reference point to apply the torque theorem, and that's what you get, right? What you do is you use the center of mass to apply the torque theorem. Now, if you did that, then negative kx has there's nothing in that because there's no lever on, right? But this force, Fs, now becomes a force providing a torque. It's the only force providing a torque about the center of mass. And it does provide a clockwise torque, which is what we need. Okay, what does that tell us? It gives us what Fs is, okay? So I have actually Fs over r, that's the torque, equals what? I times alpha. Alpha is still the same alpha. What about I here? Now remember, you have to use the correct reference point. The center of mass is your axis now, so this is ICM. See? Okay, this approach will give you the exact same answer at the end. I'm not going to do the algebra for you. please try it yourself. What you do is you solve for Fs, right? Which is ICM alpha over R, and you plug it into here. Okay, so you have to use both of these equations, linear and angular this time. You plug Fs into here. Okay, there is alpha here, there is A here. This is linear acceleration A. But alpha equals A over R. You can get rid of either A or alpha. You come up with one single equation, and it will look like this at the end. Alright, so this is the approach to this problem using force and torque. The reason why I want to use torque here is because this is a rotating problem, so you have to use torque. It's not all that difficult, but it does require knowledge for both translational and rotational motion. Now, is there a simpler way to solve this problem? Well, have we tried energy approach yet? Let's take a look. The very same problem. I'm going to do it this time with energy approach. If you have energy approach, then all you have to do is write down energy of the system. Don't worry about direction, components, up, down, left, right. Okay, E equals to what? You got kinetic plus potential, right? Okay, for a normal spring mass system, when there's only sliding going on, the only form of kinetic energy is the translational kinetic energy. That will be equal to 1/2 mv squared. Here v is the center of mass speed. Okay. In our case, there is also rolling going on, so in addition to the kinetic energy of translational motion, we also have kinetic energy of rotation. And you know how to write that down, right? 1/2 I omega squared. Now, it's not just any I, it must be ICM, as we learned in Physics 1A. And this V actually is VCM, okay? It's actually VCM, the center of mass at point O. So the only thing different is that we have an additional term for the potential energy, for the kinetic energy due to rotation of the cylinder. Now, what about the potential energy? Well, if the spring is stretched by amount x, then it's just 1/2 kx squared, right? It doesn't care whether the thing is rolling or not. It's just how much spring is stretched, and that's by an amount x. Now, if you compare this expression with the standard expression we have for mass spring system, the only difference is that there is one new term here. How do we get rid of this term? Well, actually, it's not that hard to do, because you know V and omega are related, right? So what I can do is I can replace omega with V. How do you do that? Well, omega equals V over R, isn't it, for pure rolling? I'm going to replace omega with V over R. Then I have a V squared here as well. Then I'm going to combine these two to get a single kinetic term. Okay, so let's do that. Plug this in. The second term is now 1/2 ICM and then V squared over R squared, right? Okay, so we have 1/2 m V squared plus 1/2 ICM V squared over R squared. And then, of course, plus the potential energy term, 1/2 kx squared. Alright. I am now going to factor out that 1/2 m and v squared. I'm just going to take that 1/2 out. Okay. Actually, I'm going to take 1/2 out and v squared out. What's left is m from first term, and second term is ICM over R, right? And then v squared. Plus the next term, I just copy it, 1/2 kx squared. Alright, how does this compare with the standard expression that we know? Well, the only difference is that instead of m, I have this whole bunch, right? Instead of m. I mean, the standard solution would be simply 1/2 mv squared plus 1/2 kx squared, right? But this is our effective mass, isn't it? If we call this effective mass, then we go back to the standard mass spring system, and therefore we know that this must be simple harmonic motion as well. And what's t? T is 2 pi times the square root of m effective over k effective. Here is m effective, k effective is still k. That's m plus ICM over r squared over k. Now, does that yield the same answer as we had before? Well, let's hope so. What's ICM? ICM is 1/2 mr squared, as we learned. Okay, so ICM over r squared What's that? Isn't that 1/2 m? 1/2 m plus 1 m. What's that? That's 3m over 2. Okay, so this is 2 pi 3m over 2. Okay, that's exactly the same as we got before. Now, you can see for yourself which method is easier for this approach. If you use energy here, you don't have to mess with torque, force, lever arm, positive, negative sign, nothing like that. All you have to do is to introduce one more term of kinetic energy due to rotation, and then combine these two terms from the pure rolling condition, and there you go, you get the same answer. So you see, oftentimes the energy approach is a better alternative, and this example shows that very well. Okay, another common example, an important one for simple harmonic oscillation, is what's called a physical pendulum. You know what a simple pendulum is? A simple pendulum consists of a massless string and a bob of 0 volume attached to the end of the string. That is, of course, only a mathematical simplification. No such thing really exists. In the real world, a pendulum, basically you suspend this thing at that point and pull the center of mass to the side and let go of it, it's going to start swinging back and forth. The shape and size can be arbitrary. The mass is not necessarily distributed only at the end of that pendulum. That's called a physical pendulum. This can be, and the object that you suspend can be anything you want, any real-life object. But of course, we're going to make things a little bit easier by assuming that even though the shape and size is arbitrary, it's a rigid body, therefore the shape and size does not change over time. Otherwise, it will make things more complicated for us. Okay, let us study the oscillation of this physical pendulum. To do so, we can look at energy approach, right? We can also look at force and torque approach. The energy approach in this problem will give you almost the same exact answer as the case of a simple pendulum, because all you have to do, as far as the potential energy is concerned, is to focus on how much the center of mass rises and falls. You don't have to, deal with the fact that this whole thing is uniformly evenly distributed, whatever, or unevenly distributed. Just focus on the center of mass. See how much it rises and falls. And so the answer will be pretty much the same as the case of simple pendulum, and I would encourage you to do that. You go back to the case of energy approach for simple pendulum and see how we can rework it. There's very little difference. Okay, now what I want to do here is to show you an alternative approach using torque. Why torque, not force? Well, because if you want to use force for the center of mass, then you make sure you have to consider all the external forces exerted on the center of mass, correct? Okay, there it is, gravity. And let's say the pivot point has no friction, okay? Otherwise, there's more complication. But even if there is no friction, you understand the pivot point has to support the weight of this thing, right? And so there has to be some sort of supporting force here. Do we know what that force is? Not really. It can actually vary from time to time, and I don't know what it is. Do I want to deal with it? Well, no. Nonetheless, I really have to, and here you don't really have to, because what you can do is to study the net torque about the pivot point. Okay, we can do that because it's a fixed point. What's the advantage of doing that? Well, any force going through that pivot point would have 0 lever arm, then we don't have to worry about it. So therefore, it is certainly a good idea to use the torque theorem about the pivot point A. Okay, since the contact force at that point does not enter the torque equation because there's no lever arm, the only force providing a torque is gravity. Okay, let's see, what kind of force, what kind of torque does gravity provide? Well, by definition, torque equals force times lever arm. Okay, this is the force. The lever arm, how do you figure out the lever arm? Well, you recall from physics 1A, we start from the line of action. Here's the line of action of the force, and we drop a perpendicular, okay, until we reach that pivot point. Okay, so it's from here to there, or similarly, it's from here to there. That is the lever arm, R perp. And how much is that equal to? Well, okay, so R perp, according to this right angle triangle, equals d times sine theta, right? D sine theta. And therefore, the torque, the magnitude of the torque from gravity would be R perp times mg. So that's mg d sine theta. That's the magnitude of the torque. Now what about the direction of the torque? You know the torque has two senses, clockwise or counterclockwise. In this case, if you start from this as a reference line when theta equals 0, you go this way, that's positive direction. We call this positive direction the clockwise positive direction. What about the torque? Well, obviously torque from the gravitational force is counterclockwise, so we call this negative. This is the torque. Torque equals negative mg d sine theta. According to the torque theorem, this I is measured at point O, okay, I0 times alpha. What is alpha equal to? Alpha equals to the second derivative of theta with respect to time, by definition. Let's compare this equation that we got with the standard solution, with the standard equation for simple harmonic motion. We have negative kx equals mass times acceleration, right? And you see here, just like we learned before for the simple pendulum case, you replace x with theta, okay? So the second derivative with respect to x becomes the second derivative with respect to theta. And then this time, m is replaced by I naught, okay? Or I0, the rotational inertia about the pivot point. K is replaced by mgd, so that's the effective k. So what's the only thing left? You have x, but instead of theta, which is what you expect, you have sine theta. How do I get rid of the sine? Well, we learned that before, right? You have to invoke some sort of approximation. And what does it say? Yes, it says small angle approximation. So again, theta is very small, and therefore sine theta is roughly equal to theta. Okay, I have now received this equation here, which is totally analogous to the standard one. Okay, so what I do is I replace x with theta, all right, and I replace m with I0, okay, and I replace k with mgd, right? And I get my answer. This is simple harmonic, so that could be simple harmonic as well. And what is the answer to theta? Theta equals maximum angle times cosine omega t plus delta, just like before. Omega is the square root of effective k over effective m. So this is effective k, this is effective m, all right? And let me just write down the expression for t directly, the period of the physical pendulum. 2 pi times the square root of m effective over k effective, right? Here is m effective and here's k effective. So this is I naught over m g d. Okay, this looks very different from what we had before for simple pendulum, but actually is really the same. For the simple pendulum, all we have to do is to assume that, okay, here's the pivot point, right? And here's the mass. All the masses are here. The distance between the pivot point and the mass, by definition, is d. But in the case of simple pendulum, we call it L. Remember that? Okay, and what about I0? The rotational inertia caused by the single point mass, a distance L away from equilibrium from the pivot point, we know that I0 equals to m L squared, isn't it? So for simple pendulum, let's see what that leads to, okay? 2 pi times the square root of I at point O, that's ml squared, mgd, d is just L, mgl. See? You cross out the m, you cross out 1 power of L, what do you get? 2 pi square root of L over g, which is exactly what we got before. So the physical pendulum is a more general case to the simple pendulum that we studied before, and we use the torque theorem to do that.